Swayam Prabha. Digital India. Educated India.
Hello everyone. Today we will discuss about thermoelectric effects, and as we have seen in our previous class that even in all the electronic circuits heat is generated, so it is quite important to understand the relationship between heat and charge currents basically. So we will discuss about two important thermoelectric effects in today's class, basically Seebeck effect and Peltier effect. Before going into this discussion, let's quickly review what we have seen so far. So far we have seen quantum confinement in MOSFETs, and we also discussed about the strain engineering in silicon, especially in nanostructures in ETSOI MOSFETs. And what we saw was that if we grow the channel silicon on a silicon germanium substrate, in that case we can change the band structure of silicon in such a way that first effective mass is modified such that the mobility is increased, and second the inter-valley scattering in silicon is reduced. So by using strain in proper direction, we can enhance the mobility or injection velocity of electrons in the silicon channels, and that's one of the, I would say, one of the very smart ways of improving transistor performance without changing the dimension of the transistor. So we also started discussing thermoelectric effects, and we started with this familiar expression, and this is the expression for current in a conductor. In a conductor like this, this is a semiconductor material which has contact 1 on left side, contact 2 on the right side. The current through this bulk semiconductor is given by this expression, and this we have already seen. This expression essentially comes from the Landauer's general model of transport. So what we understand here is that F1 minus F2 is an important quantity. It is actually the forcing function for the current. So if F1 minus F2 is 0, in that case the current will also be 0 and there is no electrical conduction in the circuit. But if F1 minus F2 is non-zero, in that case there is a non-zero current in the circuit. And what we also saw was that F1 minus F2 can become non-zero by number 1, voltage difference. If there is a voltage difference between terminal 1 and terminal 2, in that case F1 minus F2 will be non-zero. So this is properly understandable from this point. In this case V2, the voltage on terminal 2, is greater than V1, which is the voltage on terminal 1, and we are assuming in this case that the temperature on both terminals is equal. So in this case the if V2 is greater than V1, in that case the Fermi level of terminal contact 2 will go down, and the Fermi function, Fermi Dirac distribution function on the contact 2 will be shifted to the left side this way. So as you can see, in a small energy range around the Fermi levels, F1 minus F2 is non-zero, F1 minus F2 is positive in fact, and that way the current is positive, which means electrons are flowing from contact 1 to contact 2 and the current is flowing from contact 2 to contact 1. So the positive current in this particular discussion was assumed to be in minus x direction, because this is the x direction and we are assuming positive current from contact 2 to contact 1, which is minus x direction. Okay. So, this we have discussed in great detail now, that because of the voltage difference there can be a current in a conductor. Also, due to temperature difference also, F1 minus F2 can become non-zero, and this is the scenario. In this case, V1 is equal to V2, which means that the voltage on both the contacts is equal, but the contact 2 is at higher temperature now, TL2, which means the lattice temperature of contact 2 is more than the lattice temperature of contact 1. And in that case, what happens is that this at higher temperature, as all of us know, the Fermi function modifies, and at higher temperature the Fermi function sort of broadens. It basically becomes non-zero for a wide range of energy values. So, F2 becomes like this because T2 is now greater than T1, and as you can see, F1 minus F2 is non-zero, is positive in this regime, and F1 minus F2 is F1 minus F2 is negative above Fermi level and positive below Fermi level. Okay. And the Fermi level does not shift because of the temperature difference. Okay, so what it means is that the current, especially this kind of charge current, can be induced by two factors. One is the voltage difference, and second is the temperature difference between the two contacts. So far we have only considered the voltage difference, we have not discussed about the temperature difference in a conductor. So, that is what is the subject matter of thermoelectric devices or thermoelectric effects. So, if there is a temperature difference, which means delta TL, which is TL2 minus TL1, the difference of temperature of contact 2 and contact 1, if this is greater than 0, in that case in near equilibrium situation, near equilibrium means that this delta TL is not very large, it is still very small difference, but the contact 2 is now hotter than contact 1, but it is not too hot, the temperatures are almost equal, there is a small difference in the temperature. In that case, F1 minus F2 can be given by minus del F by del T times delta T, where delta T is the temperature difference between the two contacts, TL2 minus TL1. So, delta T is actually delta TL, which is this value. And so, what we can say here is that for n-type conductor, so if this semiconductor is an n-type material, which means that the current conduction happens in the conduction band. So, in an n-type material, this is the conduction band, this is the valence band edges, and the Fermi level is close to the conduction band, and most of the conduction happens in the conduction band. So, the conduction happens above Fermi level in case of n-type material, and if there is a temperature gradient or if there is a temperature difference between the two contacts in an n-type material, so we need to focus here, because in this regime current conduction happens, and in this regime F1 minus F2 is negative. So, that there will be a negative current, which means electrons will flow from contact 2 to contact 1 and current will flow from contact 1 to contact 2, or there will be a current in positive x direction. Okay. Similarly, in a p-type material, the Fermi level is close to the valence band maxima, and current conduction takes place at the bottom of at the top of the valence band here, and the current conducts due to holes. In this case we need to, and in this case if there is a temperature difference, in this case we need to see F1 minus F2 below Fermi level, and as you can see F1 minus F2 is positive, which means there is a current in minus x direction and minus x direction. So, depending on the I would say the doping of the semiconductor, the current direction will be determined when a temperature difference is applied on across the semiconductor. And this is very important, because let us say if we have an unknown piece of semiconductor, and in that case we do not know whether it is p type or n type. In that case what we just need to do is we need to heat on one side. Let us say we will heat the semiconductor on contact 2, and if the current is in minus x direction, in that case the semiconductor is p type, and if the current is in plus x direction, the semiconductor is n type. So we can find out about the polarity of or about the doping, the nature of the doping in the semiconductor just by measuring the current due to temperature difference. So now what if we have both voltage difference and temperature difference? So what if we are applying a battery across the semiconductor and there is also a temperature difference between contact 1 and contact 2. So in that case we need to combine the contribution of both of these terms, this one and this one, in F1 minus F2. So in that case F1 minus F2 will be given by minus del F by del E times Q times delta V from here, minus del F by del E. So this minus del F by del T becomes minus del F by del E into E minus EF by TL times delta TL. So this we derived in our previous class, if you recall. So when there is a voltage difference across the semiconductor and there is also a temperature difference, in that case F1 and F2 will look like this, the plots will look like this, and as you can see we have applied a positive voltage on terminal 2, which means EF2 is now shifted to the left side, and also we have heated the contact 2, which means F2 is now spread out. F2 is now more broader as compared to F1. So in this case, which is a very general case, F1 minus F2 will be given, or we need to consider both of these terms while calculating F1 minus F2. And please remember that this is near equilibrium situation. Near equilibrium means that the applied voltage is also is quite small, also the temperature difference is also small. We are not applying a large voltage or a large temperature difference. So with this background, what we can say is that the current will conduct because of the two driving factors. One is the voltage difference and second is the temperature difference across the conductor. And in order to properly model the current in any conductor, we need to take into account both of these parameters while doing the actual current calculation. With this, I think this is a good time to introduce a new kind of current in conductors, because electrons are particles that carry both charge and heat. Electrons carry charge as well as heat, okay, and this we discussed last time. So this is how we define the charge current, and in this case this expression becomes the expression for charge current, because we have this factor of Q here. So if we remove this factor of Q from here, in that case this will be, this expression will give us just the particle flux when there is a difference in the Fermi functions of between the left contact and the right contact. So this is a generic particle flux, or I would say the particle current, and if we multiply this by charge, it becomes charge current, and this is what we derived in the general model of transport, and this is what we use in calculating the current in all the devices in fact. But as we know that apart from the charge, electrons also carry heat in terms of in the form of their kinetic energy. So when there is a flow of electrons, apart from a charge current, there will be a heat current as well. It will be as if a heat is also flowing through the material. So that's what we need to define, but the charge current at a particular energy is given by this value just by removing the integral, and without Q this is the number of particles flowing at a certain energy E. If we put Q here, in that case it becomes the charge current actually. Okay. So, as we have seen that F1 minus F2 is or when there is a gradient in voltage as well as in temperature. So, if across a conductor we have delta V as well as delta T, in that case F1 minus F2 is given by these two terms, and if we put these two terms here, then the charge current becomes like this. So, this is the general or the most general form of the charge current, both in presence of voltage difference and temperature difference. So, both of these terms need to be taken into account, and we will discuss more about it in coming slides in after a few minutes, but let us take a pause and define the heat current as well. And in order to define the heat current, we just need to replace Q in this expression or in this expression by E minus EF. And why E minus EF? The reason for this is that generally in most of the cases, most of the conduction takes place around the Fermi level. Especially in metals, almost all the conduction takes place at the Fermi level. All the electrons are in metal, a new electron is entered at the Fermi level, or any electron exit from the Fermi level itself, Fermi level energy. Even in semiconductor, the Fermi level defines in a way the distribution of particles in a material or distribution of particles in the semiconductor. So, in order to define heat current, the amount of energy that is in access to the Fermi level E minus EF is the heat in that system. Okay. That is so this comes mainly from the metals or conductors, and if we just put replace Q by E minus EF in this expression, it will give us the heat current. So, heat current will be heat current at a certain energy E will be 2 times E minus EF divided by H TE times ME times F1 minus F2. Okay. So, please remember that this is not charge current, and that is why this is the heat current, and this is that is why this its unit will also be different. So, I will give you few minutes and so just think about what would be the units of IQ, okay, and we will come back to this in coming slides. So, this is a typical picture of conduction in a semiconductor, in which we have a semiconductor this is the semiconductor, this is the conduction band of the semiconductor, minima of the conduction band, and there might be EV, the valence band maxima, and this is the conduction band minima. So, and if so let us first draw the equilibrium picture. In the equilibrium, what happens is that on left contact we have Fermi level EF1, on the right contact we have Fermi level EF2, and if we are using an n-type material, n-type semiconductor, the Fermi level in the semiconductor will be EF, and if it is n-type, the Fermi level will be closer to the bottom of the conduction band as compared to the top of the valence band. So, this is the left contact, this is the right contact, and this is the semiconductor in between, and this is the equilibrium I would say the equilibrium band diagram of the system. And as you can see, in equilibrium all the Fermi levels are aligned to each other, there is a single uniform Fermi level in the entire device. But if there is a voltage applied on contact 2, so that EF2 goes down, there is a if there is a positive voltage on contact 2 and a current will start conducting in the material. There might also be a temperature gradient, there might be, so contact 2 might be heated. Let us say the temperature of contact 2 is TL2 and the temperature of contact 1 is TL1. Let us assume TL2 is greater than TL1, and in that case there is a net flow of electrons in the system. So, the way electrons flow is that electrons will start from the left contact, jump into the semiconductor conduction band, and from the semiconductor conduction band they will jump to the right contact Fermi level. So, in this case the heat current from contact 1 to the semiconductor is given by I prime Q1 E at an any energy E, and this is twice of E minus EF1 divided by H times TE F1 minus F2. Similarly, heat current from semiconductor to contact 2 is 2 E minus EF2 divided by H TE F1 minus F2. So, this is the way we analyze heat current in any device. When there is this term F1 minus F2 is non-zero, and in general if we consider that delta V is non-zero as well as delta T is also non-zero, in that case F1 minus F2 needs to be replaced by these terms in near equilibrium situation, and in that case the heat current can be written in this general form. So, as you can see, heat current is dependent both on voltage difference and temperature difference, like the charge current. So, we will very soon go to these parameters G, ST, TLST and K naught as well, but this discussion was just to show you that apart from charge current we also need to consider heat current when there is an electron flow through any device, and heat current is defined by replacing Q by E minus EF, and in that case both charge current and heat current are dependent on the voltage difference and temperature difference. Okay. So, so this analysis we have already done, because F1 minus F2 we have analyzed in our previous class. It is dependent both on voltage difference and temperature difference, because from this picture we can see that the Fermi function is both a function of voltage and Fermi level, and Fermi level is dependent on the applied voltage. So, it is a function of both temperature and Fermi level, and Fermi level is dependent on voltage. So, that is why the Fermi function becomes a function of both the applied voltage and the applied temperature difference across the conductor. Okay. So far just to quickly summarize, we have seen that especially when there is a temperature, when we talk about temperature difference across a semiconductor, we need to understand the notion of that there will be a notion of heat current as well apart from the charge current, and both heat current and charge currents are dependent on the applied voltage delta V and applied temperature difference delta T. And from these ideas we will come to Seebeck effect and Peltier effect later on. So, let us first analyze how the charge current looks like. So, charge current I prime E, which is the current at a certain energy E, is given by 2q by H TE ME F1 minus F2. TE accounts for the scattering transmission coefficient, ME accounts for the modes in the semiconductor, the conduction pathways in the channel, and F1 minus F2 is the forcing function for the current. Q is the fundamental charge unit, and if we do not have Q, it just becomes the particle current, number of particles flowing per unit time. So, the total current is the sum of contributions from each energy channel. So, we need to integrate this I prime E. So, the total charge current I is given by the integration of this. This differential current is given by this value. And as we now know very clearly that F1 minus F2 is minus del F by del E Q times delta V minus del F naught by del E minus EF by TL times delta T. So F1 minus F2 is dependent both on applied voltage and applied temperature difference. So if we just put F1 minus F2 in this expression and integrate this, what we obtain is if we just put F1 minus F2 here, I prime E will be 2q by h Te Me times F1 minus F2 is minus del F by del E Q delta V. Plus 2q by h Te Me del F by del E minus Ef divided by TL times delta T. So we have just replaced F1 minus F2 by this in the differential current expression. So here now this thing is known as the conductance function, and this thing is represented as St times delta T. So St actually is related to the Soret coefficient, it is related to the electrothermal diffusion, which means electrical diffusion due to thermal energy due to temperature difference. So the differential current has a contribution both from the conductance function and this Soret diffusion, electrothermal diffusion. So in order to calculate the total current, so this G prime E will be 2q square by h Te Me into minus del F by del E, and this electrothermal conductance is St prime is minus 2q square by h Te Me E minus Ef TL dE. Okay, so I leave this to you to sort of figure out to exactly come to this point, this expression, and because in this case we have been multiplying by q, dividing by q, and in that case this is what it becomes. Negative negative becomes positive, so that is why we have a positive term here. So the total charge, so this Soret coefficient S prime Te is given by minus Kb by q times E minus Ef divided by Kb TL times G prime E. So even S prime T can be represented in terms of G prime E. Even this Soret coefficient is related to the conductance function or the differential conductance of the material. So finally after integrating this expression, so the total current will be the integration of the differential current with respect to energy, and it becomes G prime E delta V plus S prime T E delta T integrated over all possible energy pathways, and this turns out to be G times delta V plus St times delta T. So where G is the electrical conductance of the system, of the conductor, of the semiconductor under consideration, and St is the Soret coefficient of the semiconductor or the electrothermal diffusion coefficient of the semiconductor. So this is the most, I would say, the most general form of the charge current through any conductor, and this has contribution both from delta V and delta T. So, we need to consider both electrical conductance as well as electrothermal diffusion, electrothermal conductance. Okay, so this is how things get modified when we consider the thermoelectric effects as well in our system. So, in the similar way, the heat current is defined as all of us know, the heat current from contact 1 is defined as 2 by H, or if just to sort of recall, the differential heat current is given as 2 by H times E minus EF into TE times ME times F1 minus F2. And if we need to find out the heat current from contact 1 to the semiconductor, we need to integrate this over all possible energy channels, and this is what it turns out to be. Similarly, from contact 2 it is, and if we assume the near equilibrium conditions, in that case F1 minus F2 is given by this familiar expression that we have, all of us have seen, and if we put this value of F1 minus F2 in the differential heat current expression, in that case this is what the heat current actually becomes like. So, just replace F1 minus F2 by this right hand side in this equation and see what you get. So, let us do a quick calculation here. I prime q, E is 2 by H times E minus EF TE ME, F1 minus F2 is replaced by minus del F by del E times Q times delta V plus 2 by H E minus EF times TE ME del F by del E minus EF by TL times delta T. So, this becomes the differential heat current in the system, and if we have a close look on this side, this coefficient apart from delta V, this is closely related to the Soret coefficient, because this S prime T in our previous derivation is given by this expression. So, this first term becomes essentially, this first term becomes minus TL times ST prime times delta V, and the second term becomes K naught prime E times delta T, where this K is now known as the electronic heat conductance, and this K naught is known as the electronic heat conductance coefficient. So, in order to find out the total heat current, we need to integrate this differential heat current over all possible energy values, and that is why we need to integrate on the right hand side as well, and the final expression for the total heat current that we obtain is this, and this is minus TL times ST times delta V minus K naught times delta T, where this K naught is given by this expression, and I will leave you leave this calculation on you, how K naught turns out to be this value. This is a very straightforward calculation and you should be able to do it. So, as we have already discussed that the heat current is also dependent both on voltage difference and temperature difference, and but there is a key distinction here, that in heat current IQ is minus TL times ST minus K naught times delta T. So, this ST appears with delta T in the case of charge current. If you recall, ST appears with delta T in the case of charge current, but it appears with delta V in the case of heat current. and that is an interesting aspect because both of these currents are sort of coupled to each other. That sort of indicate that. So now we have a decent background, decent mathematical background of both charge current and heat current in conductors. Now we are in a good shape to define one of the most popularly known thermoelectric effects, that is the Seebeck effect. And what is the Seebeck effect? Seebeck effect is essentially the development of an EMF due to temperature difference in a conductor. What it means is, if there is a temperature difference in a conductor, an EMF, electromotive force, will be developed across the conductor. In other words, a voltage difference will be developed across the conductor, and if we have the conductor open circuited, in that case we will have an open circuit voltage due to temperature difference. This is known as the Seebeck effect, which in other words means that if we heat a conductor on one end, there will be a non-zero voltage difference between two of its terminals. And now with the background that we have seen, this is not something unfamiliar, because what we have seen is that the charge current is directly proportional to delta V as well as delta T. So if there is even if we do not have any applied voltage, even if this is 0 and this is non-zero, in that case there will be a non-zero current, which means the electrons will flow because of the temperature difference. And if the semiconductor is open circuited, in that case this flow of electrons will result in an open circuit voltage, which will balance the flow of electrons because of the temperature difference. Okay? And that is the root of the Seebeck effect. So in a way, the charge current that we have discussed is actually, this Seebeck effect is a natural consequence of this idea. Seebeck effect naturally comes from here, even if we do not have any voltage difference across the semiconductor, which means delta V is 0. In that case, I is given by St times delta T, which means there will be a flow of electrons in the conductor, and if the conductor is open circuited, electrons will accumulate on one side of the conductor, creating an open circuit voltage, and that is essentially the Seebeck effect. This open circuit voltage is also known as Seebeck voltage, and the way to understand this is that is just from the Fermi function, and this we have seen in other forms as well. This is the Fermi function at temperature, F1 is the Fermi function at temperature TL1, and F2 is the Fermi function at temperature TL2, and TL1 is less than TL2. Let us assume that this end of the semiconductor is hot and this end of the semiconductor is cool, which means TL2 is greater than TL1. So the Fermi function on this side of the semiconductor will be like this red plot, and the Fermi function on the left side of the conductor will be like this. And since there is no voltage applied across the semiconductor, EF will be the same across the this conductor. So if this is an n-type semiconductor, in that case we need to consider the flow of electrons in the conduction band. And what happens in the conduction band is above the Fermi level. Above Fermi level, F1 is less than F2 essentially. So which means that F2 is greater than F1 in conduction band. So that means that the number of electrons or the probability of electrons on the right contact in the conduction band is more. The probability of electrons being found close to the conduction band energies is more on the right contact, the hot contact, as compared to the cool contact, cold contact essentially. So the electrons will try to from as we discussed in the general model of transport, this contact will try to bring this semiconductor in equilibrium with itself. So, the electrons will start flowing from hot contact to the semiconductor and from semiconductor to the this left contact, okay. And that way electrons will accumulate on this side of the semiconductor. That will leave a positive voltage on the right, the hot contact, and a negative voltage on the cold contact, and that will create this kind of open circuited voltage, okay. And if we connect any electronic system here, that can result in a current as well. So, that way we can produce an electric current by a temperature difference. Just by a temperature difference we can produce electric current. So, essentially converting heat into electricity using semiconductors. So, that is how the thermoelectric devices are made by using the Seebeck effect. We will not be able to discuss about thermoelectric devices in this course. So, what we will do is we will discuss the basics of Seebeck effect and a related effect known as Peltier effect, and essentially most of the devices work on the underlying principle of these two effects. So, if these two effects are clear, then we can understand most of the thermoelectric devices mechanism. So, if there is a temperature difference, an open circuit voltage will be developed across the semiconductor, and that is known as the Seebeck effect, okay. So, from the charge current expression, this is what we have. I is G times delta V plus ST times delta T, which means if we rearrange these terms, G times delta V is equal to I minus ST times delta T, or delta V is equal to 1 by G times I minus ST by G times delta T. So, this is the charge current. So, this is what we obtain. 1 by G, G is the electrical conductance, it is R times I minus ST times G times delta T. Now, if the two ends of the semiconductor, if the two terminals of the semiconductor are open circuited, we have not connected anything, there cannot be a flow of current, this I will be 0 in steady state. So, in that case delta V is equal to minus ST times ST by G times delta T, and this delta V will be the voltage that or the voltage difference that appears across the semiconductor. So, this is when I is 0 in open circuit case, and this term is known as the Seebeck coefficient essentially. ST by G is known as the Seebeck coefficient, which is defined as S. S is ST by G. So, what is the Seebeck coefficient? Seebeck coefficient is essentially becomes from this equation delta V is equal to minus S times delta T at I equal to 0. So, S is minus delta V by delta T when the current is 0. So, this is the technical, the formal definition of the Seebeck coefficient. This is the ratio of the voltage difference to the temperature difference when the current in the circuit is 0. So, what it also means is when we have a temperature difference across a conductor delta T, delta V of voltage difference will be produced when the conductor is open circuited, and the ratio between delta V and delta T with a negative sign is known as the Seebeck coefficient. So, this is an important I would say important thermoelectric coefficient, and all of us should be very clear about its definition as well, also its physical mechanism. The underlying physical mechanism is essentially this one. Okay. So, as we will expect that the sign of the Seebeck voltage, which is the delta V voltage, is also known as the voltage on the hot side minus voltage on the cold side, is positive for an n-type conductor, and the Seebeck voltage is negative for the p-type semiconductor. And this can also be used to determine the type of semiconductor that we are using. So, this is this we have also discussed here. Also, I would also like you to think more about it and also see how electrons will flow in a p-type semiconductor. So, in this particular example, we have taken an n-type semiconductor. So, I will recommend all of you to look into the situation when instead of n-type semiconductor we take a p-type semiconductor. In that case, how the electrons will flow when the left contact is cool and the right contact is hot. Okay. So, with this, let us maybe finish here today, and in the next class we will start with the discussion of Peltier effect. Okay. So, thank you all, see you in the next class.